afternoon, everybody. A couple of announcements. One is for review session. I decided to have it in this class and at our regular class time, so everybody can attend. So Friday would be the review session, and also distance learning student can join us. So our review session this Friday at 1 to 2. That's one thing. Next homework is due on Friday. So I know that like some of the problems, actually two of problems, ask you for sufficient statistics. Just forget about it. Okay. So sufficient statistics we haven't learned in this class, so you don't need to answer those questions. I think one is in problem 5 and the other one is problem 6. Okay, that's one thing. Another thing is for method of moment, when you want to find mu prime 1 or mu prime 2, which is this guy, if this is undefined, what I mean by undefined, it's infinity, for example, then what you need to do, you need to, instead of finding the expected value, this guy is expected value of x, if you remember. Okay, that's the definition of expected value. And for this, for some cases, expected value of x is undefined. For example, is infinity. So what you need to do in order to use method of moment, try to use a function of x rather than expected value of x directly. For example, you can use x squared. You can use 1 over x. You can use exponential of x. Okay? It's right here. Okay? Exponential of x. So something like that. Then you can, so one function which gives you a defined expected value rather than undefined expected value. And when you are trying to define your sample moment, you should also apply this transformation. For example, if you are using, let's say, exponential of x, we know that n prime 1 is summation of xi divided by n. If I use exponential of x instead, then it should be summation of exponential of xi divided by n. Okay? So what you do, expected value of x, instead of that, you use a function of it. Maybe these are the choices. And for your sample moment, you need to basically change that definition of sample moment accordingly. Okay? I think one of the questions that you have for method of moment requires this transformation.
Transformation on the expected value, do you need to do the transformation inside the PDF too, or?
Yes, no, not the PDF, because the expected value of x squared, or put it this way, that's the definition or property of expected value. Let's define an h function, any h function, anything. The expected value of h function is defined by this guy. So you just replace x with h of x and do the integration. Okay? Yeah.
Say, for example, you use like the exponential
That would be
transformation.
Mm-hmm.
Once you were done and you got like some equation for theta, did you take like the log of that? Or?
No, so it's just a set of equations. You just solve it for the parameter of interest. That's it.
Okay.
That's it. Any other questions? Okay. And before I start with confidence interval, I want to go over this example one more time. The example for uniform distribution. So let's say for uniform distribution, want to use MLE to estimate the upper limit for basically the exponential distribution. So if we do that, let me start with likelihood function of A given sample x1 to xn. What is the definition of likelihood function? It's multiplication of PDFs. The PDF for this guy is 1 over A. It has nothing to do with basically your xi. So it's 1 over A multiplied by 1 over A. How many times? N times. Okay, so it's n times of that. So it gives you 1 over A to the power of n. Is it clear? And as you can see here, if we take a derivative and try to maximize this guy, there is no x here. So if I say this guy is equal to 0, then A should be 0. And we know this is not a good estimator because the lower bound is 0. Okay? So we said we cannot use derivative for maximizing this function. Instead, we need to basically use the shape of the function here to find the maximum. Okay? So let's say we have three observations. So our random sample size is 3. This guy is 2, this guy is 2.5, and this guy is 1. Okay? Okay. So if I want to use any of these observations to estimate A, what would be the best one? So look at this function. The smaller value of A gives me the larger value of your likelihood function. So the smallest one is the best one. Okay? So what would you suggest here? It would be 1. Okay? So basically, minimum of x1 up to xn is a good estimator for your A because it minimizes this likelihood function. Does it make sense so far? Is it clear? Okay? So, but there is a problem. If I use 1, or the minimum in this case, so I have a constraint on my PDF. The constraint says all x's or observations should be between 0 and A. Okay? Look at this. All observations should be between 0 and 1. But I have 2 and 2.5. Okay? It's a contradiction. Does it make sense? So basically, the solution I got is optimal, but is not feasible solution. Okay? I need to find the best feasible solution. So what is the best feasible solution in this case? Is 2. It's the maximum one. So if I use A hat 2.5, sorry. Yeah. If I use the maximum of x1 to xn, then I can make sure that all observations in the sample is less than this guy. And therefore, it's a feasible solution. Okay? Maybe not optimal, but it's feasible. Is it clear? That's why we said this is the basically estimator for your A parameter. Are we good? Okay, now let me switch to a new topic. So this is not going to be an exam. Okay, this is for the second exam actually. Confidence interval for one population. Are you guys done with this? Can I erase it? Okay. Now, let's say we have a population again with two parameters, mu and sigma squared, which is mean and variance. Let's say normal population. And we know that in reality, we don't know those values. That's why what we do, we collect a sample, then we define an estimator, in this case, mu hat, which is a function of, let me use h for this guy, would be better, x1 to xn, to estimate mu. Okay? And we learned how we can define this function. Method of moment, maximum likelihood. There are two methods that we learned to define this function. Okay? And we also learned how to compare different functions or different estimators. Okay? But here is one problem. We know that, for example, in this case, best estimator would be x bar. Okay? Now, if I ask you, what is the probability that x bar exactly estimates your mu or mean parameter in the normal population, let's say? What is that number? Anybody? So what is it? 0. Exactly. Why? Because we know that the point estimation probabilities, the point probabilities are equal to 0 for continuous distribution. Okay? So basically, I have a number for a parameter, but probability of exactly finding your actual mu is equal to 0. So you cannot claim that that x bar, let's say it's 5, represent your mu, unless you have infinite sample size. In that case, you can say x bar is exactly mu, or unless you collect all, you observe all the population. Does it make sense? Okay. Now, so point estimation is not basically enough. So what should I do? I should use this point estimator and define an interval, okay, and say with some confidence, let's say 95%, I can claim that this interval includes my actual parameter, because I know x bar cannot estimate mu, okay, cannot exactly find the value of mu, but I can use x bar to define an interval which, with some confidence, I can claim that interval includes my mu. Okay? This interval called confidence interval or interval estimates. That's what we want to do. Is it clear? Any questions so far? Okay. Now that's the time that you see the connection between different chapters that we learned so far. So we learned how to define point estimator. We learned something else. You remember? What is the distribution of this point estimator? Which we call it what? Sampling distributions. Okay? For x bar is what? Normal with this mu and sigma squared divided by n. For s squared was chi-square distribution. Okay? Now what I'm going to do, I'm going to connect these two. I said, I know the distribution of x bar or my point estimator or s squared, then I can use this information to build this confidence interval. That's the connection between the sampling distributions, and that's the reason that you learn sampling distribution and point estimator. So sampling distribution in one hand, point estimator in the other hand, then get together, we can find confidence intervals. Okay? So let me see. So we will learn how to define a confidence interval for normal distribution under different scenarios, known sigma, unknown sigma. For non-normal data, we also can do that when we have large samples. Do you know why? We can use central limit theorem for that. And we also learn how to find sigma squared confidence interval for normal distributed data. Any questions? Okay. So as I said, This is the population. We do the estimation. And what we want to do now, use the distribution of point estimate and come up with some intervals, which we call confidence interval, in order to have a better estimation for mu and variance. Okay? And as I said, this L and U, both of them are functions of your random sample. And you will learn how to define those functions, the lower bound and upper bound. Any questions so far? Okay. Let's start with confidence interval for mean, okay, for mu, and when sigma is known. Okay? So I have x1 to xn. I use x bar as point estimate. Sigma squared is known. This guy is known. And I want to define the confidence interval. I think some of you have seen the confidence interval for mu. I just want to show you how we can derive that confidence interval, that you've maybe used it before. It's very simple. The method called pivot method. And what we do, we use the property of x bar, or sampling distribution for x bar. We know that it follows a normal distribution with this mu and this variance. Therefore, x bar minus mu divided by standard deviation, we call it z, follows what? The standard normal distribution. Okay? For a standard normal distribution, let's see, this is a standard normal distribution. This is 0. I can define 2 points where alpha over 2 is here and alpha over 2 is here. So I'm trying to find a confidence interval with the confidence of 1 minus alpha. For example, if I'm talking about confidence of 95%, my alpha would be what? 0.05. Okay? Sometimes they call it significance level. Alpha, 1 minus alpha confidence, alpha significance level. Okay? So I can define 2 points, and I divide alpha in 2 parts. Okay? One for the left side, the other one for the upper side. What is this guy here? You remember, it's a point that probability after this point is alpha over 2. What is it? Z of alpha over 2. Okay, that's the definition of Z function. How about this guy? This is symmetric. If this is Z of alpha over 2, this should be negative Z of alpha over 2. Okay? Because it's symmetric around 0. Any questions so far? So what is the probability in between? This probability? What is it? 1 minus alpha, which is the confidence that I need. So what I'm going to do, simply, I say probability of Z between these two numbers is 1 minus alpha, which is the confidence I need. Okay? Then I know Z is this guy. So I write it down as probability of this. Instead of Z, I use x bar minus mu divided by standard error. Z alpha over 2 is 1 minus alpha. Okay? Is it clear? Any questions so far? So what is the next step? Multiply by this guy and then subtract mu. Subtract x bar. So what I'm trying to do, I want to isolate mu here. I want to do some multiplication and summation in order to have mu here and everything else in this side and this side. Why? Because I want to define a confidence interval for mu. So mu should be in between. How I can do that? I multiply by this guy. So it would be probability of this multiplied by standard error, and then I add and I subtract x bar, okay? I get, oops, let's use different color. Z alpha over 2 which is equal to 1 minus alpha. Okay? So what is the next step? Just multiply by a negative. And at the end of the day, if you do that, it's all the way down. You guys can see it or not? Maybe I can write it down here. Probability of Z alpha over 2 minus, I'm sorry, x bar minus, that's easier to show. X bar minus Z alpha over 2 times the standard error. This is mu in between, and x bar plus Z alpha over 2 sigma over n. And this guy is 1 minus alpha. Okay? So now I have mu here. I have my lower bound, and I have my upper bound with the confidence of 1 minus alpha. And as you can see, everything is known, because if I get a random sample, I can calculate x bar from that random sample. Sigma is known. That's our assumption. N is the sample size, and Z alpha over 2 is basically from table or chart of normal distribution. Does it make sense? What happened here? Yeah, I guess so, but we don't need this guy. We already have the presentations. Okay, does it make sense? So what you get is this guy as the lower bound, and this term as upper bound, with a confidence of 1 minus alpha. Okay? If the main assumption is for normal distribution, as you can see up there, for normal distribution. However, if the x doesn't follow a normal distribution, but your sample size is large enough, like greater than 30, then you can use central limit theorem and still get the same confidence interval. Any questions? Is it clear? Okay, good. So we have one example. Actually, a very simple example. I'll go over that example. Let's see. I have a solution here. Okay. So we are doing like some standard test based on a procedure, a standard procedure. We have 10 measurements for impact of energy, okay? And these are the measurements that we have. So if we assume that the measurements follow a normal distribution, and based on the sample, we want to see whether how we can find a 95% confidence interval for the mean of impact energy, okay? And the standard deviation is given. So what we need to do, first we need to find x bar, which is summation of xi divided by n. This case would be 64.1 up to 64.3 divided by 10, and you get 64.46. Your sigma is given, which is 1. So what you need to do, you need to find your 1 minus alpha is 95%. Your alpha over 2 is 0.025. So you need to find z of 0.025, which is 1.96. Okay? Yeah. And then your lower bound is this guy minus 1.96 times your standard deviation divided by n. Your upper bound, the same thing, plus 1.96, 1 over square root of 10. So if you calculate this, you get 63.84, 63.84, and 65.08. Okay? Any questions? So that's the confidence interval. So although my x bar is 64.46, my confidence interval is kind of like wider and symmetric around x bar, and it says with a confidence of 95%, your mu would be between these two. Yep.
Symmetric for symmetric distributions.
Exactly. It's only symmetric for normal distribution, t distribution. It's non-symmetric for chi-square distribution, which is basically for sigma squared confidence interval. That's actually true. Any questions? You good? Can anybody tell me what is the interpretation of a 95% confidence interval? How can I interpret that confidence interval? So can I say the probability of mu between these two numbers is 1 minus alpha or something else?
There's a 95% chance that your true population mean lies between those two bounds.
Okay, but let me give you something. If your lower bound and upper bound is random variable, every time that you collect the sample, those numbers are going to change. Okay? So how do you basically explain that one?
Multiple.
And what happens?
Different
You
confidence
get different
intervals.
confidence intervals? And what? It's actually correct. You want to say something? You want to add something to that?
95% of those new samples would have a mu between those.
Exactly. So that's the correct interpretation of it. So every time that you collect a sample, you get a lower bound and upper bound. Okay? And let's repeat this guy for many times. Let's say for 100 times or 1,000 times. And we don't know actual mu. But if we know actual mu, then some of these confidence intervals, let's say this is the first sample, and this is the first confidence interval, which is 63.84 and 65.08. Some of this confidence interval includes the actual mu. Okay? Some of them don't, like this. So what is the expected number of those confidence interval which include the actual value of mu? It's 95%. Okay? That's basically is the interpretation of 95% confidence. So if we do it for a long for so many different samples, then 95% of those confidence interval includes the actual value of mean, and 5% do not. Any questions? Okay. Now, let's say choice of sample size. We know that if distribution is not normal, then what we need to do is to have a large sample, like 30. But if the distribution is normal, what would be a good choice for sample size? I can use the error of estimation in order to find the appropriate value for n. So the error estimation is what? X bar is estimated for mu, as you can see. So the difference between these two with the absolute value, absolute sign, then is going to be your error. Does it make sense? Okay. So let's say you want your error to be smaller than a number. So you want your error to be smaller than, here in this case, E. Then you need this number of samples. Okay? So if you want to have your estimation error be less than E with the confidence of 1 minus alpha %, then your sample size should be this guy. So this is known, and your E is the number that you give. Okay? So let's say if I want to have E equal 0.1, I just replace E by 0.1. But how I can derive this n? So let's say this is the confidence interval that we have. Okay? Confidence interval is basically x bar between, x bar minus z alpha over 2 sigma square root of n. Okay, now what I'm going to do, I want to find this guy, okay? Mu minus x bar. Then this is between two quantity. Okay? And I can show that the absolute value of this is less than x bar. Oops, sorry, this is not x bar. Z alpha over 2 square. I'm sorry, greater than. Okay? That's the definition of absolute value. So what should I do? I solve it for n. First, this is E. So let's do a square. Z alpha over 2 sigma n. This is a square. Then solve it for n. N should be greater than this guy. Okay? So that's what you have on the slides. So basically, I'm using the estimation error, point estimation error, in order to find the required sample size. Is it clear? Any questions? Okay. So I'll give you a couple of minutes to work on that example. It's actually related to the previous example. You have the information here. And it says, we want to find an appropriate number of samples or a specimen under some errors. You have a question? Sure.
Trying to interpret that last sentence where it says has a length of it at most 1 joule. Or 1. Is that a difference? Or like
Yes.
From the, okay.
Yes. Yes. If you read the problem statement in the previous example, then that length is basically the error. It's the difference between the actual. Actually, I made a mistake. This length is the length of confidence interval. If you read it again, it says to ensure that the 95% confidence interval on mu has a length of at most. So length of confidence interval, which means u minus L. This is the length of confidence interval. Because you have two numbers here, the length means upper bound minus lower bound. Anybody got a number? 16? Okay. So it says the same procedure in example 8.1, 8-1, and supposes that we wanted to determine how many specimens or sample size basically must be tested to ensure that the 95% confidence interval on mu, blah, 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 has a length of at most 1 joule. So this is U, this is L, so length is U minus L. In this case is X bar minus this guy minus X bar, which is the lower bound. Then what is this number? 2 Z alpha. Okay? So it says this number should be 1. Write it down here. This number should be 1. Okay? So what is your error? Your error is something like this, which is, this is error, or absolute value of this guy, which is Z alpha over 2 okay? So your error is in this form. This is U minus L. So what would be your error? Is 0.5. Okay? So you have your error. Your N is defined as Z alpha over 2 sigma error squared, which is 1.96 times 1 times 0.5 squared. This is 15.37. So actually your N should be greater than that. Since N should be an integer number, this would be 16. Okay? Is it clear? Any questions? Do you know how I get this guy equal to this guy? Just forget about this part. Look at this. Okay? That's just x bar minus mu. And actually this should be less than, but anyways, so that's, let's say, just the equality part we consider. So that's the error. In this form, this guy is 1, so this should be 0.5. Go ahead.
Couldn't you solve the 2z times sigma over root, and you'd set that equal to 1, and
Okay.
so if you solve that for n, you also get 16.
Yeah, you're right. That's much easier. I guess book wanted to, yeah, that's actually correct. Book wanted to use this as an example of error, so wanted to show that error is involved here. But I guess you're right. You can solve this one for n and then get the same result. It's a very lousy example, I would say. Any questions? Are we good? Okay. Sometimes we just want to have like one-sided or confidence interval. Sometimes we just want to have a lower bound, and sometimes we want to have upper bound. In this case, we use similar upper bound and lower bound. We just replace alpha over 2 with alpha. So what happens, we just push all alpha into one side rather than two sides. Okay? Can anybody give me one example in reality, in the application, that we only care about upper bound?
Output of a conditional signal, so the 0.
Yes, that's one example. Another example is waiting time of the customer. Okay? So we define an upper bound. We don't want this go above some number. Okay? We don't care about lower bound because the lower the better. Okay? How about the lower bound? Only lower bound. One example would be the strength of a part. Okay? Tensile strength. The higher the better. Okay? So we have a lower bound, we don't have upper bound. Again, we can use the same equations for non-normal case when n is greater than 30. One example, I guess we have a couple of minutes, so I can go over this example. So we are testing the strength of disposable plastic beverage container, and the strength are normally distributed with known standard deviation. So basically when it says known standard deviation, it means sigma. When it says from historical data we have, or from previous knowledge we have sigma, or standard deviation equal to some number, this is sigma, it's not S. Okay? Because when sigma is unknown, instead of Z distribution, we are going to use t-distribution. You will see on Friday or next Monday, actually. A sample of 20 plastic containers has a mean strength of 246. So this guy is what? This is sigma. This guy is 246 is x bar, not mu. Okay? So x bar is 246. Sigma is equal to 15. What else? We have 20 sample, and 1 minus alpha is 95%. So what is alpha? Alpha is 5%. So Z alpha would be 1.645 from table. We want to have a lower confidence bound, okay, because this is strength, that makes sense. So lower confidence bound is this guy. You know, similar to this, just replace alpha over 2 with alpha. This is the lower bound. And x bar, which is 246 minus 1645, sigma 15 divided by square root of n. That's it. That gives you the lower bound. Any question? Is it clear? From the normal chart. So, am I making a mistake here? Let me see. So, 95% is this guy. Okay, because this is Z alpha. Z alpha means probability after this point is 5%. Probability before this point is 95%. Okay? And normal distribution and normal chart here, it gives you probability before this point. So before this point is is right here and here. So it's in between. Okay? Because this guy is 94, 95, this is 95.05. So if you do interpolation, is a number between these two guys. So this number is 1.64, and this number is 1.65. If you take the average, it would be 1.645. Does it make sense? Any questions? See you on Friday. Oh, by the way, I have your homework graded here, homework number 2. You can pick it up. Sorry. Yeah, sure. Just give me a second. It's categorized based on your last name, the first letter of your last name. No, not based on your grades. So this is yours? Okay. I can leave it here. Yeah, sure.
When I was working on Province Street,